Hello, good morning students. Today we'll discuss about the register set in the 8051 microcontroller. You know what is a register? Register is nothing but the storage device. It is made up of flip-flops. You know flip-flop is the 1-bit memory cell. That means single bit of information you can store in flip-flop. So like that, group of flip-flops. Registers are having different sizes, 8-bit, 16-bit, 32-bit registers. So whenever we say 8-bit register, that means there are total 8 flip-flops that are used. So the registers are used for storing the bits. In 8051 microcontroller, most of the registers are 8-bit. There are few exceptions which are 16-bit registers. Now let us start discussing the register set of the 8051 microcontroller. Here you can see the special purpose registers that are used in the 8051. That includes accumulator A, which is the 8-bit register. Then B, another 8-bit register, mainly used for multiply and divide during the multiplication and division in these two instructions, along with accumulator. So that is limitation. For multiply and divide, you have to use either only A and B registers. You cannot use the any other general purpose registers. So that is the function of the B register. Accumulator is actually the bottleneck. You know that one of the operands should be always in the accumulator for arithmetic and logical operations. Let us suppose you want to add the two numbers. Then one number should be in the accumulator and second number you can store in some other register. After execution of the add instruction, the result will be stored back in the accumulator. Okay. So like this, for all arithmetic and logical operations, one of the operand means what? Data. That should be in the accumulator. Then PC, now see, this is the 16-bit register that is used to keep the track of the program instructions. That means program counter PC that holds the address of the next instruction that is to be executed. Okay, because you know the microcontroller executes the program instructions in sequence, one after the another. But whenever there is a branch, let us say calling the subroutine, or whenever there is a jump instruction, or whenever the interrupt occurs, in those situations, the PC contents are updated with the new address and the execution transferred to the subroutine, either interrupt subroutine or whatever the subroutine that is called, right? Or using the jump, go to the branch address. So that is, the PC contents are automatically updated in that case. But normally, it always holds the address of the next instruction that is to be executed in sequence. So automatically, while executing the current instruction, the PC contents will go to the next, updated automatically. Okay. Then, but depending on the size of the instruction, you know, there are 1 byte, 2 byte, 3 byte, 4 byte instructions. Depending on how many memory locations are required to occupy that instruction, the instructions are classified as a 1 byte, 2 byte, 3 byte, 4 byte instructions. In 8051, most of the instructions are single byte, requires only one machine cycle, but there are a few like multiply and divide which requires more than one machine cycle, right? So whenever accessing the external memory, then requires more number of machine cycles. Well, that is the use of the program counter. Then next is the stack pointer, 8-bit register. Basically, it is used to hold the top of the stack. The stack pointer, mainly stack is what? Nothing but the set of memory locations that is used for temporary storage. When it is utilized, either by the user. Whenever you feel that the number of registers are less and you want to use the registers in your program again, so what you can do, you can save the current content of registers onto the stack temporarily, use the same registers again for your manipulation, and whenever your work is finished, you can pop that from the stack and the original contents will be retrieved back in those registers. So the stack pointer always point to the top of the stack. Then DPTR, this is another 16-bit register. Earlier we had seen the program counter, and now here the DPTR, data pointer. Actually, there are two parts, DPH and DPL, that is the lower byte and the higher byte. You will see later on. So it is used to access the external memory as a pointer. Then PSW, this is again 8-bit register, or is the program status word. We'll see the format of the PSW in the next. Now here it shows the general purpose registers. They are stored in the 4 register banks. So in the RAM, 128 bytes of RAM, which is on chip, you can find that lower memory locations that are occupied by the 4 banks, then 0, 1, 2, and 3. And there are 8 general purpose registers in each bank. You can see in this next slide. Here the bank 0 is having 8 registers from R0 to R7. Similarly, bank 1, bank 2, and bank 3. Now, these are used for general purpose. By default, bank 0 is selected. That means the 8 registers from the bank 0 are available for the user. But when you find these are less, you want few more. So there is always the option of selecting the another bank. And how that bank selection is done? Using the 2 bits in the PSW, or is the program status word, which is shown here. So these 2 bits, RS0 and RS1, that are used for selecting the bank. So this is the format for that 8-bit PSW, program status word register. You can see the 8-bit format. The explanation of this, let us discuss. P is nothing but the parity flag. The parity flag is set when the accumulator has the odd parity. And if accumulator is having even parity, that means number of ones in the accumulator. If those are even, then the parity flag will be reset, 0. Okay? Set for odd, 0 for even. Mainly used for error checking method, parity flag. The next bit is reserved. The next is OV, means overflow flag. Whenever the result is not fitting into the destination, that means suppose the destination is 8-bit, and if you try to save the 16-bit result in that time the overflow flag will set using the arithmetic operations. For example, divide by 0. In that case, divide overflow will occur and the overflow flag will set. Now these 2 bits, as we discussed, are used for bank selection. RS0, RS1, bank 0. Then 0, 1 means bank 1. 1, 0 means bank 2. And 1, 1 means bank 3. By default, bank 0 is selected, but later on, by, let us say, if both bits are 1, then bank 3 will be selected. That is how those bits can be used. Next is the F0 bit, that is called the general purpose flag bit. Next is AC, auxiliary carry flag, mainly used in the BCD or arithmetic. BCD is binary coded decimal. In the BCD addition, you know, if there is a carry after the 3rd bit, right? Then from D0 to D3, then if there is a carry at the D4th bit, the auxiliary carry flag will set, okay, in the BCD addition. As far as the carry flag is concerned, whenever there is a carry out of MSB, let us say addition of 2 8-bit numbers and there is a carry After the addition of MSB bits, the carry flag will set. So mainly used in the arithmetic, logic, and Boolean operations. Okay. So this indicates the status, whether the carry is there, whether original carry flag is set, whether the overflow is there, whether parity, odd or even. That's why it is called as the program status work. Then here is the list of the all SFRs called as the special function registers in the 8051 microcontroller. Accumulator, B register, then DPL and DPH data pointer, two divided into two parts, 8 bit each, lower byte and the higher byte. Then these are related to interrupts, IE and IP, interrupt enable register and priority register. Then these four are for ports, parallel ports, port 0, 1, 2, and 3, four parallel ports. Then these are the timer registers, load count in those. Let us say TL1 and TH1 used for timer 1, loading the higher byte and lower byte of the count. Then TH0 and TL0 for timer 0, right? Higher and lower byte count. So two 16-bit timer counters. And these two SFRs are used to deal with the timer counters, TCON and TMOD. We discuss the bit pattern. Then stack pointer used to hold the top of the stack. Then ESBUF used as a serial buffer during the serial communication. SCON serial control register, again in the serial communication. ESW just now we discussed is the program status word, and PCON is called as the power control register. Now in these you will find that some of the registers are having star mark. What is that? Star mark means those are bit addressable registers, right? So what are the bit addressable SFRs in the 8051? Accumulator, D register, IE register, IP register, four ports P0, P1, P2, P3 registers, latches, then TCON, then SCON, and PSW. So these are the bit addressable registers. Means you can individually set or reset the bit of that individual bit of that register. Let's say you want to set the third bit of the port 1. So you can set P1.3 bit using the set bit instruction, right? Set or clear. You know the instructions that are available in the instruction set to set or reset the individual bit. So that is the advantage of this 8051 microcontroller. The rest of the registers are not bit addressable. Then here the same list is shown again. Only difference is here their internal RAM locations that are given for all the SFRs. Let's say accumulator can be accessed at E0H address. All these are having unique addresses in the memory map in the internal RAM. Let us say you want to access the ports at ATH. You can access the port 0 for parallel data transfer. You can use these ports as an input or output. So through these port addresses, ATH, 90H for port 1, A0 for port 2, and B0 for port 3. So like that, using the port addresses, you can communicate through ports with the other peripherals, parallel data transfer, right? So these are the memory locations for all the SFRs that are there in the 8051 microcontroller. Next, the SFRs related to timer counter, mainly TMOD and TCON. Here you can see the bit format for that. In the TMOD, the lower 4 bits are for timer 0 and higher 4 bits are for timer 1. In the TCON, the lower 4 bits are for the interrupts and the higher 4 bits are for the timers. Now here, M0 and M1 are used for selecting the mode. There are 4 modes: mode 0, mode 1, mode 2, and mode 3. So that can be decided using the status of these 2 bits, M0 and M1. from 00 to 11 to select the appropriate mode. Then C oblique T bar bit is used to define whether you want to use it as a counter or timer. The gate bit that should be enabled in order to use the corresponding timer counter. Same for MSB 4 bits, only difference is those are used for timer 1. Similarly, here the TCON register, the lower 4 bits are actually used in the interrupts. Now here the higher 4 bits, TR0 and TF0 correspond to timer 0, TR1 and TF1 correspond to timer 1. These 2 bits are used for TR means timer run control bit, and this is the flag bit. Whenever this bit is set, timer will, this is mainly used to issue the start command, okay, to the timer. And whenever the count rollovers from all ones to all zeros, automatically the overflow flag will set. So this is that flag bit. So whenever the overflow occurs, the TF bit will be set. That is the use of the TCON register. Okay, we issue the start command, and after finishing the count, setting the corresponding flag bit. Then to deal with the serial port, there are 2 SFRs, SCON, called as the serial control register, and another is SBUF, called as the serial buffer, which is the simply a shift register, the data, 8-bit data that can be received during reception in that SBUF, or the data that is to be transmitted over TXD that can be written in the SBUF during transmission. SCON, mainly the serial control register. Here you can see the bit format for that. Now RI indicates receive interrupt and TI indicates transmit interrupt. The 2 bits for setting the interrupt during reception and the transmission. Now RB8 and TB8, these are the bit, 9th bit in the mode 2 and 3 of the serial communication. During reception, whenever the 9th bit comes, that will be here in the RB8. However, during transmission, it is transmitted through TB8, the 9th bit. We know that can be used for parity check, etc. Then REN indicates the receive enable bit to enable the receiving data, and SM2 bit is mainly used in the mode 2 and 3 only of the serial communication, that is used for multi-processing communication, right? And SM1 and SM0, these 2 bits, MSB 2 bits are used for mode selection. Once again, if 00 means mode 0, 01 means mode 1, 10 means mode 2, and 11 means mode 3. And serial port can operate in the 4 different modes, right? Well, already we discussed about the modes of the serial port. Now, start. So that is about the SM0 and SM1 bits of the SCON register. Now, there is one PCON, that is called the power control register. Only the MSB bit of that is used for serial communication, that is the SMOD bit, that is mainly used to decide the baud rate. If the bit is set and if the bit is reset, the baud rate can be doubled if the bit is set. Okay, so that SMOD bit is mainly used to decide the baud rate in the serial communication. Now the LSB bits, you can see here IDL and PD. These are 2 bits which are used for power control in the 8051. IDL means whenever the clock to the CPU is frozen, And at the same time, the on-chip peripherals like the timer counter, interrupt, or serial port that will remain functioning. Only the clock to the CPU that is gated off. That time it is in the ideal mode. However, the contents of the all registers and SFRs that will be maintained will not change. In the power down mode, actually, the clock signal to the CPU as well as the peripherals, on-chip peripherals like timer counter, interrupt, or serial port, that is gated off. So CPU will enter in the power down mode if this bit is set. However, again, the contents of registers, SFRs that will be maintained, right? So that is the difference between the power down and the ideal mode. In power down mode, everything is not functioning, that is CPU as well as the clock to the on-chip peripherals, that is stopped. However, in ideal mode, the CPU will enter in the sleep mode. However, the rest of the on-chip peripherals that will continue functioning. Okay. So that is the 2 bits used for power control in the 8051. Now these two are the general purpose flag bits, G of 0 and G of 1. So that is the bit format for the PCON SFR, right? Now next, the SFRs related to the interrupts. You know, there are 5 interrupts in the 8051 microcontroller. Now there are 2 main SFRs called the interrupt enable register and the interrupt priority register. Here you can see the format for interrupt enable register corresponding to the 5 interrupts. This is for external interrupt 0, timer 0, external interrupt 1, timer 1, and the serial port interrupt. If the bit is set, that means the interrupt is enabled. If the bit is 0, that means the interrupt is disabled. So to enable or disable the individual interrupts, these bits of the IE register are used. And at MSB, there is a EA called as the enable all. This is a very important bit. If this bit is 0, that means none of the interrupt will be recognized. It will disable all. So in order to use these interrupts, this bit should be 1, and then you can individually mask or unmask the interrupts. IP is the interrupt priority register. In this, you can assign the high or low priority to the individual interrupts. Again, for external interrupt 0, 0 means low priority, 1 means high priority. Similarly, for timer 0, priority for external interrupt 1, priority for timer 1, and priority for serial port interrupt. So only 2 priority levels, either high priority or low priority, that can be assigned to the individual interrupts using the IP, okay? Interrupt priority register. Now, what is the priority within the level? That means the priority order. You can see by this arrow, E0 is having the highest priority. That is, external interrupt 0 is having the highest priority in the 8051. Then to the timer 0, then to the external interrupt 1, then to the timer 1, and the serial port is having the lowest priority. There are 2 bits, RI is receive interrupt and TI is the transmit interrupt. Means the serial port can generate the interrupt either due to the transmission or due to the reception. That's why there are total 6 sources, though there are only 5 interrupts in the 8051. Now in the TCON, the LSB 4 bits are used for interrupts. Here you can see IT0 corresponds to the timer 0 interrupt, IE0 corresponds to the external interrupt 0, IT1 corresponding to the timer 1, and IE1 corresponds to the external interrupt 1. Okay, so rest of the bits are for timer count that we already discussed. So these bits are used for timer 0 and 1 and external interrupt 0 and 1 interrupt bits, right? So that is about the SFRs related to the interrupts in the 8051 microcontroller. Well, that's all. So those are about the register set of the 8051 microcontroller. We discussed about the special purpose registers like accumulator, B register, then stack pointer, program counter, and DPTR, and then PSW. Then we discussed about the flag bits of the PSW. Let's see in the general purpose registers, how they are arranged in the banks. There are total 32 general purpose registers. Each bank is having 8 registers. And then we discussed about the special function registers. In that we had seen some are bit addressable and some are not bit addressable. And then we discussed about the SFRs related to the interrupts, then serial port, timer counter, and we also discussed about the PCON or control register, that is whether to operate the 8051 in power down mode or ideal mode. So that is all about the register organization or register set of the 8051 microcontroller. I hope all of you understand that. Thank you. Thank you very much.